Hello again. Tonight's presentation is white dwarf pulsars, and we'll get into detail as to what that means. You've probably heard of white dwarf stars. It's a kind of star. You've probably also heard of neutron stars that are rotating fast and spewing out radio pulses, and so we call them pulsars. They're both stars at the end of their existence when they're fuel is basically exhausted and they collapse. If you're small enough, you collapse and you produce a planetary nebula. Like, poof, that's the ultimate destination of our particular star, the sun, is it will collapse down to a white dwarf producing a planetary nebula. The sun is spinning at a rather slow speed now, and when it shrinks down, much like an ice skater or a skater on roller skates, as they spin, they pull their arms in, they spin faster and faster. So as it reduces its diameter from its original spin, it'll get faster and faster. But if it's not, big enough when it collapses, it won't spin really fast, but it'll produce, the reason why they call them a white dwarf is it produces light from the infrared all the way up through the visible into maybe some UV. That's why they call them a white, because they're white. But they also have a magnetic field, like our sun has a magnetic field. And when a star collapses down, the magnetic field gets stronger and tighter. Stellar mass or an average size star will collapse down into a white dwarf. And then if the star is somewhat larger, the gravity will collapse it down even further, and you'll be compressing atoms down to the point where the neutrons take over and you get a neutron soup or a neutron star, and their magnetic field's much stronger and they spin much faster. The fastest one we have ever observed is spinning 716 times per second, and it has an intense magnetic field, and the beams of magnetically induced energy coming out the poles, that's what produces the pulsating radio or the lighthouse strobing effect. And that is mostly in the radio bandwidth and not so much visible. But what if you had a star that was kind of midway between the two, or you had something that was going to be a white dwarf, but interacted with something else that kind of made it a midpoint or a combination of the two? So that's what we have here is a white dwarf pulsar. So if you have a white dwarf and it collapses down and wants to spin, it has a magnetic field and it gets a stronger one. And when it collapses down and it's rotating slowly, it might have a rotation period that might be seconds to minutes. So if it collapses down, it's got a magnetic field, it's not rotating as fast as a pulsar. That's essentially a white dwarf pulsar, still emitting broadband. So in addition to its normal white range, it would also be emitting up into the UV and X-ray and down into the radio bands. And so if they found one of these unicorn-like things, they would have to characterize it. So they'd need multiple observatories looking in their specific bandwidths to say, can you see at that location something, whatever wavelength, whatever flux intensity, can you see it there? They've been doing this. And if you remember, we did a presentation a while back about multispectral observing, where somebody's running an observatory in the gamma bandwidth out, orbiting in space, and they detect something. They go ask their friends down on Earth or on other deep spacecraft, hey, I see it in gamma. Do you see it in X-ray? Do you see it in infrared? Do you see it in visible? Do you see it in radio? And they're starting to click together. So white dwarf pulsars is a noteworthy multispectral observing process. So the first time they kind of found one of these, they had been thinking they should exist for about 5 decades. The first time they observed one was in 2016 in the constellation Scorpius. It's in the Milky Way. It's about 380 light years from Earth, and it's called AR Scorpii. So that was the first one that gave them a clue that these kind of white dwarf pulsars can exist. But they didn't, when you find your first unicorn, some people will doubt you, and other people will go, well, nobody wants to do the trench work to characterize it as to all the different bandwidths that it emits in. But we found another one. So in June of 2023, the South African Astronomical Observatory and the South African Radio Astronomy Observatory detected another one of these unicorns. It's a pair of stars, a white dwarf and a red dwarf, which is kind of an oddball that you'd have these two stars in very close proximity to one another. It may have been a capture. I don't know, that they haven't done any analysis on that. But the white dwarf would be at the end of its life, and the red dwarf, they'll last billions of years. So the red dwarf could be at the beginning or the middle of its life. And there's other postulations about how white and red dwarf stars can play matter off of one another. You can look it up. It's called stellar vampires and stellar zombies, where one star draws off of another and changes itself, detonates, which changes the other one back. And so the first one that grabs matter off of one, that's, the vampire. And then when it blows itself apart and resurrects the other star, that's the zombie. So, but we're just going to talk about white dwarf pulsars tonight and steer clear of the vampires and zombies. So this white dwarf star is about 773 light years from Earth. It's in the Milky Way. The orbital period of these two stars, this binary pair, is about 4 hours. Given that these are stars and they're rotating that close together that fast, that's a lot of energy that's cranking around between the two of them. It's got a very long name, which is for the Julian coordinate system in equatorial. So they dropped off the fractional parts because apparently there's no other stars in the vicinity. So it's now just J1912-4410. So the right ascension is 19 hours, 12 minutes, and the declination is 44 degrees, 10 minutes negative. They analyzed from the emissions that the magnetic field of this white dwarf pulsar should be about 1 million times greater than the sun, but the mass is about the same as the sun. So this is a star that might have started out as what they call a stellar mass star, a star about the size of our star, the sun, and when it ran out of energy, it collapsed down to this white dwarf. And from the spectral emissions of it, they can tell that it's been around a while. This white dwarf may have been around for billions of years because its temperature has dropped. It's basically, when a white dwarf first becomes a white dwarf, it's still hot from just having been a star. But you add a few billion years and it radiates the heat out to space. It can't radiate sunlight, but it radiates energy out into space. And when it cools down to a certain level for a stellar mass star, a white dwarf is going to be said to be quite old. So this one is quite old, which pairs it up with the red dwarf star, which can be quite old. So this binary system may be quite old. But what about emissions? This is where the multispectral, multiple observatory, multiple instrument stuff comes in. We'll start down at the low energy, long wavelength with the MeerKAT radio telescope array in Australia. And they looked in the L band, which is 856 to 1712 megahertz, and they detected it. So they logged that as, we've observed it, it's in radio, it's in the L band. And then the new technology telescope at Silla in South America, in Chile, they looked at it in near infrared using an instrument called ULTRACAM. And yep, they spotted it in near infrared. They spotted it visually by the Southern African Large Telescope, the SALT telescope, so confirmed in visual. And then they used the Hubble Space Telescope's Cosmic Origins Spectrograph, or COSS, to look at it in UV from 111 to 215 nanometers. So very high energy, very short wavelength. And then they tasked the XMM-Newton X-ray space telescope, and they found it in X-ray as well. So this white dwarf pulsar is emitting radiation from radio, infrared, visual, ultraviolet, up to X-ray. So it's very, very broadband emissions. And by looking at the spectrum of it, they've detected that not only is it producing just emissions consistently. It's also got, due to its magnetic field, pulse emissions. So as it sweeps around, you get a pulsar-like effect. And they're guessing, they made the postulation in their analysis that this thing has polarization pulsations. So the magnetic field, as it spins, may actually be drawing up and tightening the pulsar beam. So when they receive it in radio, they actually receive both sides of the polarization, the positive and negative. And they've also seen it in spectral line pulsations. If you've looked at pulsars and their emissions, as the pulsar beam goes sweeping past you, relativistically speaking, there is a frequency shift, kind of like a red shift, blue shift. Coming at you, it's blue, and then going away is red. So it shifts to shorter wavelength and then longer wavelength. And they're seeing that in the spectral emissions as they analyze the emission as the sweep goes by. They're saying that's normal for a pulsar, but they're also seeing gaps. So as it sweeps, they won't receive anything for a brief period of time, and they'll start receiving again, which may mean that the tilt angle of this particular white dwarf pulsar, as it has the red dwarf next to it, it's spinning, emitting, and the red dwarf, as it orbits every 4 hours with it, is kind of like occulting it, it's blocking it. So the gaps in the spectrum may be because the two are swirling together. Maybe in another few million years, we might have a gravity wave event as the two spiral into one another. So we have a rotating pulsar radio emission about every 5 minutes. It spins about 300 times faster than the Earth, which is very slow for a pulsar. Most of them are typically fractions of a second. The fastest are called millisecond pulsars because each pulse is separated by a millisecond of time. It's broadcasting in radio, and we can see gaps as it spins. So, maybe it's the white dwarf occulting it's the red dwarf occulting the white dwarf. Maybe it's the gravity of the two affecting one another. We have to do more study. Now, you may not have heard of this, but there's a thing called the dynamo model. It's a mathematical model of stars that interact with one another as they're orbiting, that whoever has the greater gravity. In this case, if you have a pair of dwarf stars, the one with the greater gravity is the bigger one. But it doesn't have to be diameter bigger. It just has to have higher density, greater gravity. And as they're swinging around, it may be that one was captured and one is swinging around the other, or their center of gravity may be directly between the two or beneath the surface of one, so it's slingshotting it. And as the one with greater gravity can draw stellar matter off of the other one, in this particular case, they believe that the white dwarf is drawing stellar matter from the red dwarf. If it was the white dwarf drawing stellar matter from a red supergiant, it would draw off enough matter to create an accretion shell on the outside of the white dwarf, and it would supernova, or it would go nova. And when it does, that's the vampire and zombie scenario. But it starts out as the dynamo model of one drawing from the other. And it may be that this white dwarf, that's a white dwarf pulsar, had it not had the red dwarf nearby, it may have just been a typical white dwarf. But because it has the red dwarf nearby in close proximity and they're orbiting one another, and the white dwarf can draw off the red dwarf, and that twists the magnetic field tighter, that may be how you get a white dwarf pulsar. Is it won't do it all by itself. You have to have another star interacting with it, but we have to do more analysis. So in conclusion, white dwarf stars are a thing. Neutron stars are a thing. Seems like we've got this new intermediate category where it's emitting radiation from radio all the way up through X-ray, and we're going to call those things white dwarf pulsars. But is it really only that because of its interaction with another star closely orbiting with it? But we won't know until we figure this out as to what the limits are. Most of our mathematical limits that we have defined on astrophysics are based upon single items, like What's the smallest white dwarf? What's the biggest neutron star before it becomes a black hole? They're all single object limits. This particular one may be, because there's two things, what we would think of as what's the biggest white dwarf that isn't a neutron star. That may change the formula, but we won't know until we do more observations. So far, white dwarf pulsars, we have two confirmed, but we're still analyzing what they are. There's another thing out there called strange quark stars. Quark matter that is made up mostly of strange quarks. It's been postulated, we think we might have one, but nobody's gone back to confirm it. Then if you take it to the next degradation step, that would be quark matter stars, but instead of the strange quark, they're built upon the very much higher energy, shorter lived top quarks. And so far they're saying it's theoretically possible for there to be a top quark star, but we don't think they would exist for very long because in our, colliders, we don't see that we can make top quarks happen. We just can't make them last for very long. So maybe it's a failed black hole, a neutron star that's bigger than neutron stars should be, and it collapses down into a strange star. And the particular kind of strange star goes from strange quark to top quark, but never makes it to black hole. Or maybe that's what a black hole is. We don't know. Because we don't know on the inside of a black hole. That's all theoretical now. And the other one, which we'll talk about soon, is a black dwarf star, which is a white dwarf star that has cooled down over billions of years. And that's just theoretical because some people say billions of years. Some people say that's not far enough. It's got to be trillion years. And if you say, I found one that's, 800 billion years, no, it's got to be trillions of years. Well, until we find one, we won't really know. Ultimately, what it's saying is there are more things between heaven and earth than are dreamt of in your philosophy. We need to go out there and look for them. And once we find them, confirm they exist, and then characterize them. Know all about them.
Some of these things are going over my head and trying to figure out which ones you're telling me are theoretical and which ones actually we know about. And like if I was going to talk to somebody tomorrow and I say a white dwarf star is a thing, but
yes,
I wouldn't have anywhere else to go from there. Is that a fact, or is this a hypothesis? Or
well, when I say
that's different than a pulsar. And the pulsar is sort of like what we're questioning, right?
A white dwarf pulsar. We're not questioning the existence of pulsars. So when I say something is a thing, yes, they're matter of fact. Yes, they're more than mathematical. They're not a postulation. We observe them. So yes, there are millions of white dwarf stars in the Milky Way galaxy itself. And there's probably also many hundreds of thousands, if not low millions, of neutron stars in the Milky Way galaxy. So those are a thing.
White dwarf pulsar?
Yeah, that's the thing that so far we've confirmed that two of them are the right size and have magnetic fields and are producing broadband emissions across all spectra like a white dwarf would, but they've got radio emissions and they're sweeping by like a lighthouse, which is more in keeping with a neutron star or a pulsar. So it's kind of a white dwarf and kind of a pulsar, but it's not a neutron star. So it's kind of between the two. And we have two of them confirmed, and we're still characterizing them. So white dwarf stars that behave like pulsars, yes, they've confirmed two of them, but they don't know whether to think of them as an intermediate point between a white dwarf and a neutron star that is a pulsar, or is it a special kind of white dwarf because it interacts with another star, be it a red dwarf or a red supergiant, and that's the thing that gives it the magnetic field tightening and the energy emanations to make it a white dwarf pulsar.
It's because it's interacting with another
star, very close proximity to it.
And right now, the things that we have out there aren't interacting with another
No,
star.
the two that we found so far that we're calling white dwarf pulsars, they both have a red dwarf companion. So they're in
And
binary.
we've known about red dwarf pulsars for a while, right?
No, red dwarfs are not pulsars.
I
We've
mean,
known about red dwarfs. We've known about
okay,
white dwarfs.
okay. And both of those have been around for a while.
Yes. And in fact, red dwarfs have been around for 1 billion+ years longer than our sun.
And the fact that I'm saying being around, that doesn't mean that, like if we find out that white dwarf pulsars are in fact more than two, that
Mhm.
doesn't mean that they just happen to be found. And now we know that there wasn't before because we didn't know they were there. That means that they could have been there.
Yes, that it's much like infrared and ultraviolet light. They were there before we ever discovered them. We didn't invent them. We had to
Exactly.
create the technology that allowed us to observe them. So we now have the technology to look at a white dwarf in multiple spectrals. So we can look at it radio, infrared, visible, ultraviolet, X-ray, and even gamma if we wanted to. So we can look at a particular star in all these different forms of electromagnetic radiation, and we can see that a white dwarf will have a certain band. It'll fit in a certain band. A pulsar will fit in a certain band. But now what we have is a white dwarf pulsar that kind of merges the two bands together, and it's very broad emission.
Mm.
The quark stars, we have one that some people are saying is a quark star, but they're not saying what kind of quark it is. They're just postulating that it's probably a strange quark, a strange type quark. You've got up and down and bottom and top and strange, and you've got a couple of different kinds of quarks, which are subatomic particles. And the idea is that if you have a regular star, like a stellar mass star, and it gets at the end of its life, it collapses down to a white dwarf and blows off a planetary nebula shell. Well, the next step up in size, the next further down degeneration of the stellar matter, instead of it being a white dwarf, it becomes a neutron star, because the electrons and protons and neutrons all get compressed down so tightly that you wind up with neutrons and electrons, and the protons get converted into neutrons. And if you take that even tighter, eventually you'll get to a black hole. But could there be a midpoint on the way to degenerating, tighter, compressing further, that it's kind of a midpoint? And they're saying that that's what a quark star is. Your neutrons, which are made up of quarks, get compressed even further, and it just becomes what they call a quark soup. And you don't even have neutrons anymore, you just have quarks. And the gravity is so intense that it's just a soup of quarks. Well, the quarks would naturally want to differentiate themselves, and the higher energy, higher mass quarks would win out. And so you'd go from top and bottom to strange, because that's kind of the next step up. So they're postulating that this one star that they found is a strange type quark star. But I say, and I postulate this, that, and there's a couple other people doing this too, that why stop there? If you can see things coming down a curve, why just stop there? Why not take the curve down to the next point? The next point down would be a top quark star, and then the next point degeneration down from there would be a black hole. So you can see along the curve of denser and denser and crushing particles down to subatomic particles, and crushing subatomic particles down to their next no longer divisible state, and you find out this curve. So we have to keep looking, look for more things, and eventually we'll discover that there's more things out there than we thought would be possible.
Is it going to make a difference on our traveling through it?
We don't have the technology to travel through it.
I know, but we don't have the technology now.
Yes.
And we don't, but we have technology to get into space.
Yes.
And go to the moon.
Yes.
And so are we looking at all these different things as to how they're going to affect different things that we do? Is there any, like, I don't think there is anything that we have to worry about on travel to Mars, maybe.
They're far enough away that even the pulsar radiation isn't going to dramatically affect the Earth. We can detect it in radio and other bandwidths, but it's not going to wipe out all life on the planet or anything like that.
If we travel to Mars, would we be getting closer to it?
Not even a small fraction closer. These things are hundreds of light years away, and a single light year is about 6 trillion miles. So 300 times 6 trillion is the closest one they found so far. We can observe it. We can detect electromagnetic radiation coming from it in different spectra, but it's very, very weak by the time it gets to us. So it's kind of like, if we ever get that warp drive stuff working, that might be an interesting place to visit.
Also, yeah. I would say, given the vastness of the universe and how much there is, if one of anything is found, the odds are that there's lots more.
That actually works in other aspects of life. If you're in your house and the exterminator hasn't come in the last 6 weeks and you find one ant or one roach, there's going to be other ones out there, but I've only seen one.
Yeah.
Same sort of thing. If you find a particular type of stellar object and you classify it and it doesn't fit your categorization that you have defined, I have to give this one a new kind of identifier. It's a pink dwarf or a purple dwarf or whatever. Once you find one of them and you properly confirm its existence and you categorize it, there's probably more than one. You just haven't found it yet.
Yes.
How do they get their funding for this, though? I mean,
internationally, everybody's tax dollars at work.
Okay, but do they have to put out a proposal and say, what is the benefit to mankind, right?
Yes, you don't get to use multi-million or multi-billion-dollar astronomical instruments, be they on the ground or out in space, unless you first put together a proposal. You have a lead scientist called the principal scientist be the lead author of a proposal, why you want to use our billion-dollar, James Webb Space Telescope, what you want to observe, and what you're going to gain out of observing it. And then you file that proposal with a review team, and then the review team goes, no, I don't think so. Or, we've got 50 people all wanting to do the same thing. You guys get together and narrow it down to 3. Or, wait a minute, you want deep infrared? The James Webb Space Telescope does not see in deep infrared. Go file that with, a different telescope. Or that might be better viewed in ultraviolet. Go talk to the Hubble folks about their ultraviolet sensing capability. So,
did they just come up with this white dwarf pulsar by accident?
No, there are survey telescopes like Gaia, which is out at Lagrange Point 2, along with a couple of other telescopes. And all it does is just goes, it sweeps up and down the sky, and it logs everything it can detect. And then it has artificial intelligence and machine learning that goes, okay, I'm looking for one of these is not like the other. So I'm looking for anything new and different. And it finds things occasionally. And when it does, then they tap on the shoulder of all the other research teams on all the other observatories and space instruments and go, hey, I saw this in visual light from a large optical telescope in South Africa. Could somebody go look at it in ultraviolet and infrared? And then they'll create proposals for looking at it with other instruments in other electromagnetic bandwidth and see if they can see it. And if they can see it, then they'll consolidate their findings and go, okay, we have a white dwarf that is emitting in radio and ultraviolet, which is unusual for white dwarfs. Does it have a magnetic field? Okay, we'll look at it in radio and we'll do a spectroscopic analysis of the emissions from it and see if there's anything unusual. And that's where they found the polarization of the signal and the twisting of the signal and the gaps in the spectrum.
But they didn't have to go and get any, because you did mention that earlier. And I find that interesting. But I'm thinking, like, how are they getting funding for this? I mean, it's not easy to get funding, right?
No, it's not easy to get funding. So think of it as these are the things that have bubbled to the top as projects that got approved and they got the funding to do them. So they got the instrument time and they got the personnel funding to do the observation and the processing of the resultant data to come away with a conclusion, and then they can publish that. Remember, it's publish or perish. So they're all the time looking for new projects and they'll be piggybacking. So for example, if you're a scientist, a research scientist in South Africa, and you see that the SALT, the optical telescope, saw this white dwarf from the Gaia research, and you said, hey, we also control another telescope here in South Africa. Can we see it in that band? So you kind of like tap your friendly neighborhood radio astrophysicist on the shoulder and go, hey, you guys are in control of MeerKAT. I've got a proposal that got approved and I got some observing time. And now why don't you guys go look at it in radio using MeerKAT and see what you see? So they're piggybacking one on top of the other.
But then they have to get, once they get this, like,
yes,
we want to take some of your time and have you look at this. They got to get approval for that too then, right?
Yes, that's why these multispectral coordinated observations to do the data reduction can take years.
Yeah.
So remember, they first found the first one of these in 2016, and now we're at 2023, and we're just now sort of ticking off the box of all the other kinds of observing we can do.
The first time they saw a white dwarf pulsar was when was that?
2016.
Okay, 2016.
Yeah.
That's not that long ago, actually.
7 years, come on.
Well, some of these things take long. I mean,
yes, and it has nothing to do with the efficiency of the technology or the fact that the target that they want to observe is not currently visible, because that could be 6 months to a year just because we can't see it from where we're at. If you remember the James Webb Space Telescope presentation I did, if you want to see a particular thing out in space, the Webb telescope is hanging with the Earth in its orbit around the sun. And if the thing you want to see is out off in that direction and the Earth is currently on that side of the sun, you can have the wonderful infrared telescope that can't see what you want to see. You got to wait until it swings around to the other side, which could be a minimum of 6 months. Now,
and so during that period of time, they're getting their funding to be able to see it.
No. They're arranging their funding, but their funding may not actually start until the window for observing and data reduction opens up. So in the meantime, they've got to be working on a different project that they've already got the funding. They're already doing the observing.
Yeah, crazy.
So you've got to have multiple spinning plates at the same time. And that's how this stuff works. Now, I will say that if you spot a near Earth object, like an asteroid that's got an orbit that in 50 years will cross the orbit of the Earth around the sun, you can get people's attention and you don't have to wait for funding, because the program to analyze the trajectory and the orbit for near Earth crossing things, because it's an Earth hazard, that funding is assured. So for the people that say, I found an asteroid that I don't see in the catalogs, and it looks like after seeing 3 or 4 observations of it, I calculated the rough orbit, and the rough orbit says that's going to cross the orbital plane of the Earth, and therefore we need to characterize and more finely resolve its orbit. There's full-time funding for doing that. So all you have to
I'm glad to hear that.
Well, there's an old joke that the number of people that are actually analyzing near Earth objects that could pose a threat to the Earth is equal to the number of people hired for a 7-day shift at a McDonald's. One McDonald's. So think about that for a moment. If you have 3 people on a shift and you have 3 shifts per day for a McDonald's that's open 24 hours, that's 24 people plus, let's say, a manager, 25 people. So the number of people that are looking out for things that could wipe us out is about 25 people.
Oh, really? Wow.
Planet-wide. That's the number of people whose day job is look for things that are going to hit the Earth. So they've got a constant backlog of amateur astronomers thinking they found some new, near Earth object that's crossing the orbit of the Earth, and you need to go look for this one. And if they find something and they characterize its orbit, and yes, it does seem to be a threat, and yes, it seems to be big enough that it might be at least a city killer, then they will task radio telescopes to act like radar telescopes, and they'll send radio pulses out to the asteroid, and they'll send them fast enough that they can actually watch the asteroid turn, so they can judge not only its orbit, they can judge its rotation, and in radio, they can actually see major surface textures of the asteroid. They used to do that with Arecibo until it went bye-bye, and now they do that with a collection of some radio telescopes being used as radio transmitters and array telescopes being used as radio receivers, and that's how they image near-Earth objects now.
I'm thinking that it doesn't sound like many people for 25, but are we looking at like near miss? I mean, they would have more people if they thought there were going to be more near miss that were actually going to hit us, and then they'd have more people observing, and they already have determined that these are very far away. A lot of these near miss are like going to be years away before they get into our atmosphere near us.
Well, as they're moving through space and they pass big things like they may loop around the sun or go past Saturn or Jupiter, when they do that kind of thing, their orbit slightly changes. So once you find one of these things, you have to keep it on your active list and constantly, whenever you get the opportunity, monitor for orbital changes.
Yeah. So how many people do you think should be watching out for these things if you had the power?
I would say minimally thousands.
Oh, really?
So what they're counting on heavily is the amateur optical astronomer community, because they're the people that are finding most of these near Earth objects. So you get trained as an optical astronomer, you're watching the sky, taking pictures, and you're taking pictures of a particular constellation, and you do a wide field, and you notice a white spot, and then you run it through software, and the software says, I have no idea what star that is because it's not in my database. And then you take another picture 3 days later, and the star moved. It's like jumping across the screen every 3 days, and that would be an asteroid or a comet. If a comet's far enough away, it won't have a tail, so it'll look like an asteroid. So you just go, well, maybe it's a comet, maybe it's an asteroid, but I know that it's an object moving across the sky. And once I get 3 or 4 points, I can calculate its rough trajectory. And if that rough trajectory in the next 100 years is going to cross the orbital plane of the Earth, so you have to do astrometry, you have to do orbital calculations of multiple bodies. Once you determine it's going to be crossing, file that with the appropriate authorities, and any member of the public can file these things. So the first thing that they do is go, okay, guys, is it already in the catalog? Yeah, we know about that one. Thank you very much for your input. We'll add it to the confirmation list. Or if it's, hey, we've got a new one, let's get the team working on this one, and they'll pick certain telescopes that they can task, drop what you're doing. I don't care if somebody's got the approval and schedule for this. We need to do some images tonight of that part of the sky, because as the Earth turns, you're going to be on the night side tonight for looking at that part of the sky. So we're going to
But wouldn't it make a difference about time-wise, though? If you say, oh, this is going to pass us in 100 years, that's what our calculation is.
Yeah.
I don't think that it would be as much of a, we have to do this tonight thing as if it's 50 years from here or 25.
No. It's the Earth rotates every 24 hours.
Right.
If you notice that it's something you haven't got in your catalogs already, then you want to characterize the orbit of it to know whether or not it's going to affect the Earth at any point in the future. So the first thing you need to do is gather more data. And
Okay, because you had said that they had a trajectory of it being
no, the
100
amateur
years.
does. The amateur astronomer does.
Right.
When you turn it over to the professionals, they're going to want to do their own calculations.
Okay.
If we're going to determine whether or not this is a threat to the Earth, we're going to want professionals to do the observing. Yep, it looks like it's something we don't have in our catalog from the rough orbit that we've got. So we need to further confirm the orbit to see if it's going to be Earth crossing or not. And so we have to stop what we're doing, go find the instrument that's going to be in the dark sky facing in that direction tonight, get some images so we can characterize it, and then we'll do that every 3 days for the next 3 to 10 days. But when you do that, you'll either be using a survey telescope, or you'll be using a telescope where you took somebody else's time in order to do your analysis, and they just get bumped. And sometimes that's just what happens. It's kind of like I go do a research project. I get scheduled for time on Mauna Loa on the Keck observatories, and they have a cloud event. And sorry, clouds tonight. No observing for you. Your proposal just gets canceled, and file again. Hopefully, you'll get lucky again in the future.
Do you think more and more people are becoming amateur observers?
Yes. How
Well,
many more? How many more? I can't tell you, but David Levy, who's a guy that has found lots of asteroids and comets, he actually has instructional books and webcasts and things like that that will teach amateurs how to spot new things.
And now that equipment is becoming more and more affordable.
Oh, yeah. Big telescopes that are simple Newtonians are getting cheaper. The cameras are getting cheaper. The software is available for free download. So amateurs, it's not their rocket science, their brain surgeries for amateurs.
That's good for us because the confidence is going to get higher and higher.
Yes.
That something would be found if it's dangerous.
Yeah. Better yet, we can find that Apophis is not going to hit us in 30 years.
And that our population is improving. What is it? Growing anyway, right?
Yeah.
So,
well, we're going to wind up wiping ourselves out for a laundry list of reasons well before we get a knock from outer space.
you think so? Yeah. You think?
Yeah.
It's close. It's close. We don't know.
I just see trends. I'm a systems guy.
It's wonderful what we've been able to accomplish and be able to see in space. And I'm hoping for the positive and the good guys to come out.
The saying is that necessity is the mother of invention.
Yes.
I think that saying came from the people that were told, go invent something. We got a problem, go solve it. And then when they solved it, the management team went, necessity is the mother of invention. Okay, so we've done our conclusion. Now we'll go over to the links page. So a white dwarf star, a neutron star, which is also a radio pulsar, and then the example of this second one they found that's a white dwarf pulsar. And then for those people that want to see the actual, well, how do you know they confirmed? Well, here is the publicly accessible reports from the various radio, infrared, ultraviolet, X-ray observations. And thanks for watching. Comments? Questions? Any comments before I stop recording? I will stop recording.